Hello everyone, welcome to Sai Tutorials. Welcome to Sai Tutorials Jamkandi. So in our classes, regular classes as well as online classes are available. Please join us and learn more. So dear students, in the previous session, we have discussed some concepts related to the second chapter, that is electric potential and electric potential energy, equipotential. So in today's session, let us move towards the next concept related to your subject, that is capacitors. So before going to this concept, let me discuss a small thing that is related to your syllabus and which is a basic phenomenon. So let me discuss. Okay. The concept is electric conductor. Electric conductor. Okay. What do you mean by electric conductor? See, the before going to the concept capacitors, let me discuss some concept related to your syllabus, that is electric conductor. See, the substance, what do you mean by electric conductor then? See, the substance which allow electricity to pass through them is called electric conductor. See, the substance, note down, the substance which allow electricity to pass through them is called electric conductor. Electric conductor. See, the substance which allow the electricity to pass through them are called as electric conductors. Okay. Now, let us discuss some properties. Okay. Some properties of conductor. Some properties of conductor. So, what are the some properties of conductor? What are all the properties of conductor? Let us study in this class. See, the first and foremost important property, that is the electric potential inside the conductor is zero. See, whatever the electric potential, okay, electric potential inside the conductor is always zero. Okay, so whatever the electric potential inside the conductor, suppose if you consider any conductor, so in that the electric potential, it is denoted as EV inside, okay, inside the conductor is always zero. Okay, the electric potential inside the conductor is always zero. And second most important is the surface of a charged conductor is equipotential surface. See, I have told you in the properties of equipotential surfaces, the surfaces, whatever the surface of charged conductor, charged conductor is a equipotential equipotential surface. Okay, the surface of a charged conductor is a equipotential surface. The first one is the electric potential inside the conductor is zero. The surface of a charged conductor is a equipotential surface. Suppose if I consider any charged conductor, okay, any charged conductor, the surface, this is a surface, okay, and this is a surface, okay, and this is a surface. This is the surface area. The surface of a charged conductor is equivalent, is a equipotential surface. So whatever the surface is there, no, it is a equivalent potential, equipotential surfaces. So in this only, at the surface of a charged conductor for electric field is normal to the surface of a conductor at each and every point. So whatever the surface of a charged conductor, okay, this is the surface of a charged conductor for electric, okay, conductor for electric field is normal. Normal means perpendicular. Okay, am I right or not? This is the perpendicular surface for this. Normal to the surface of a conductor at each and every point in the surface. So whatever the surface that is present, know that the surface of a charged conductor. So the electric field is always normal to that conducting surfaces. Okay. See, the interior of conductor can have no excess charges in static situation. The inferior of conductor, okay, whatever the conductor can have no excess charges. In a conductor, if there is no any excess charges, it is said to be in a static, okay, static situation. When it will be in static situation, the inferior of, sorry, the interior of conductor can have a no excess charges. In such situation it is going to be in a static situation. Now the next is the electric potential constant throughout the volume of a conductor is same as on the surface of the conductor. See, I have told you that if there is no excess of charges inside the any conductor, okay, if there is no any excess of charges in the uh, inside the conductor, then it is will be in the static charges. Then electric potential is constant, okay, in such electric potential is constant throughout the volume of a conductor is same on the surface of the conductor. Suppose this is a value. See, this is a value, whatever the charges are. Suppose if the charges are present inside the volume, okay, the volume of charged conductor is always equal to the whatever the charges present outside the surface. I mean, the electric potential is constant throughout the volume of conductor is same as on the surface of the conductor. Suppose it can have this more number of charges. It can have the more number of charges, then also the number of charges is also the electric field is also same as in case of inside the volume as well as on the surface of it. But and also the condition is if there is no excess charges inside the conductor, then it will be static, and also the outside the surface is also it is going to be a static phenomenon. The next is the electric field at the surface of a conductor. See, the electric field at the surface, the electric field at the surface, the electric field at the surface of conductor can be written as E bar is equal to sigma into epsilon naught into n cap. This is the expression for electric field at the surface of the conductor. So these are all the properties of electric conductor. These are all the properties of electric conductor. So now another important thing that I am going to discuss today is, what do you mean by, these are the basic phenomenon relating to the concepts. Okay, that's why I'm deriving this. Electrostatic shielding. Okay, what do you mean by electrostatic shielding then? See, the field inside the cavity of the conductor is zero is called electrostatic shielding. I have said that suppose if you consider the electric conductor, the field, whatever the electric field inside the cavity of the conductor is going to be zero. Okay, is called as electrostatic shielding. Suppose if you consider the conductor with a cavity, no charges inside the cavity of the electric field. Inside the cavity is zero. So whatever may be the charges on the conductor can be, and suppose let me consider electrostatic shielding, like let us consider a cavity like this. Okay, it is a cavity. It is having no charges. It is having no charges inside the conductor. And if there is no charges, then electric field is also zero. Am I right or not? Okay. And whatever the charges outside the surfaces are like this, outside the cavity are like this. And suppose if you consider the Gaussian surface, okay, suppose if you consider the Gaussian surfaces like this, here also whatever the charges are going to be zero, then electric field is also zero, then charges outside the Gaussian surfaces are like this. Am I right or no? Then according to the Gauss law, we can derive pi is equal to surface integral of E bar into ds bar. So electric field inside the cavity is zero. That's why the Gaussian surface, Gaussian surface is also zero. From the above in conclusion, any cavity in a conductor remains shielded from electric influence. How the formation of these electric charges will form here? This is the concept what we have discussed. Okay, if there is no inside the charges, then electric field is also zero. Then how the charges are formed outside the surface of the, I mean on the surface of the charged conductor, this is the concept, right? So by the electrostatic shielding, by the electrostatic by the electrostatic shielding, this is the important phenomenon that we need to keep in mind. They will ask in some competitive exams like NEET, JEE, CET. Directly they won't ask, but indirectly they will ask the phenomenon. You need to apply there. Okay. So coming back to the concept, that is capacitors. Okay. Capacitors. What do you mean by capacitors then? So I have told you what do you mean by conductor, what is electric conductor. So capacitor is also a conductor. Okay, capacitor is also a conductor or a group of conductors separated by an insulator. Okay, they are separated by an insulator. So before coming to the concept, I will say something that it is a conductor. Capacitor is a conductor. So, or a group of conductors separated by an insulator. Separated by an insulator. The capacitor is a device. It stores the electric charges in the form of electric potential energy. See, that's what I'm going to say. So it is a device. Capacitor is a device. The function of capacitor is it is, but what is a capacitor? I mean, what do you mean by capacitor is a thing? So it is a conductor or a group of conductors separated by an insulator. Suppose this is a conductor separated by a insulator. This is whatever the separation is there, no? It is a insulator. What do you mean by insulator? Which do not allow the electricity to pass through it. Those are called as insulators. Okay. So this is a basic concept. Okay. Suppose these are the conductors. Let us consider this is positive Q charge and this is negative Q charge. Okay, I have told you that it is a capacitor is a device. It stores the electric charges in the form of electric potential. Okay, electric potential in the form of electric potential. Okay, so potential difference between the two capacitors. Also, I have the potential difference between the two capacitor is called as potential of a capacitor. Potential of a capacitor. Now, coming to the concept. So when a conductor is charged, the charge spreads on its surface. Okay. So if you consider any conductor, the charge spreads on the surface. If the conductor is smooth, it retains the charge for considerable time. Thus, a conductor can be used as a store charge. Okay. So the charge spreads on its surface. If the conductor is smooth, okay, if the conductor is smooth, it retains the charge for the considerable time. Okay, it will retain the charge for a considerable time. Thus, a conductor can be used to store charge. Okay, the ability of a conductor to store the charge is called as capacitance. Okay, the ability of a conductor to store the charge is called as capacitance. I have told you that a capacitor is a device. It stores the electric charge in the form of electric potential energy, that is denoted as V. So the potential difference between the two charges is called as electric potential. I mean potential of a capacitor. I have told you that uh, if the charges are present, those are directly proportional to V. Okay, then directly proportional constant, to remove the directly proportional constant, I will write CV. Okay, then by replacing the C is equal to Q by V. This is the expression for capacitance of the capacitor. Okay, this is the expression for capacitance. Okay, the charge on the capacitor is a charge on any plate. I have told you that charge on the any conductor or the capacitor is a charge on any plate. Okay. The unit capacitance, the SI unit of capacitance is Faraday. Very, very important. Keep in mind, the SI unit of capacitance is Faraday, that is Farad. I mean Faraday is one of the scientists who derived the expression for the capacitance. So the SI unit of in the name of his in the name of the scientist Faraday, the unit of capacitance is Farad. So 1 farad is a capacitance of a conductor. Okay, if its potential rises by 1 volt when a charge of 1 coulomb is added to it. So SI unit of capacitance is farad. So 1 farad is a capacitance of a conductor if its potential rises by 1 volt when a charge of 1 coulomb is added to it. Okay. The next concept is capacitance of a spherical conductor. Capacitance of a spherical conductor. So suppose consider a spherical conductor of radius r, its capacitance C is equal to 4 pi epsilon naught into r. This is just keep in mind capacitance of a spherical conductor which is having the radius r, its capacitance can be written as C is equal to 4 pi epsilon naught into R. So if the capacitor is filled with a dielectric of relative permittivity. So in the concept of dielectric, I'm going to say in the detail. So just take it. If the capacitor is filled with the dielectric of relative permittivity of the if there is a medium, okay, then the capacitance can be denoted as C is equal to 4 pi epsilon naught into epsilon R into r is a radius of the conductor, spherical conductor. See, when if you consider the spherical conductor of radius r, its capacitance is going to be C is equal to 4 pi epsilon naught into r. If the capacitor is filled with a dielectric of relative permittivity, so epsilon r is equal to C into 4 pi epsilon naught into r. Okay. Uh, so let me have some basic things that related to your topic. Here, at any instant, okay, let us consider at any instant charge on the capacitor is directly proportional to the two conductors of the capacitor. See, whatever the conductor is there, no? So at any instant, charge on that capacitor is directly proportional to the two conductors of the capacitor. Okay, if C of the capacitance, the capacitance of the capacitor, it is denoted as capacitance of the capacitor. Okay, capacitance of the capacitor, and C does not depend on Q and V. So if the charge capacitor is directly charge on the capacitor is directly proportional to the two conductors, C is the capacitance of the capacitor, and C does not depend on Q and V, but it depends on only shape, size, and nature of the material. Okay, nature of the material between the two plates. Between the two plates. Okay. Now, the SI unit. I have told you that SI unit is Farad. Sorry. The SI unit is Farad. That is denoted by the letter F. See, suppose for small units, it can be denoted as microfarad or picofarad or nanofarad, like this. It will go on like this. And symbols are the capacitance of the capacitor can be denoted by the symbol. This is okay. This is for a fixed capacitor. See, the capacitor of the capacitance of the capacitor is denoted by like this. It is for fixed capacitors. Okay, and this is for variable capacitors. This is for variable capacitors. And the dimensional formula. Okay, the dimensional formula of capacitance of the capacitor is m to the power of minus 1, L to the power of minus 2, T to the power of 4 into A to the power of 2. Okay, this is the dimensional formula for capacitor. Now coming back to the concept, that is principle of a capacitor. What do you mean by principle of the capacitor? See, an earthed conductor kept close to a charged conductor decreases the potential potential of the charged conductor. Hence, for a given Q, the corresponding V is small. Hence, the ratio is equal to C is equal to Q by V is large. That is, the capacitance of the conductor increases. See, what do you mean by the principle of capacitor is an earthed conductor. Okay, whatever the conductor, let us consider it as earthed. Okay, an earthed conductor kept close to a charged conductor. Okay, kept close to a charged conductor decreases the potential of the charged conductor. So if you keep the earthed conductor with charged conductor, it will decreases the potential of a charged conductor because it is placed near to the charged conductor. The earthed conductor will decreases the potential of the charged conductor. Hence, for a given Q, hence for a given charge Q, the corresponding V is small. Okay, the corresponding V is small because by contact, I mean by keeping the charged conductor with the earthed conductor, that earthed conductor will decreases the potential of the charged conductor. So, hence for a given Q, the corresponding V, it is small. The ratio, that is C is equal to Q divided by V, is a large. That is, the capacitor will be large. If the capacitor will increases, the potential will decreases. That is, the capacitance of the conductor increases. This is just keep in mind that in the given equation, C is equal to Q by V. If I consider the one earthed conductor, I keep this earthed conductor with a charged conductor. The potential of the charged conductor will decreases. Why it will decreases? Because I kept the charged conductor with a earthed conductor. Hence, for a given charge, if the capacitance of if the capacitance increases, then the potential will decreases. This is a capacitance of the conductor increases. So I have said you in the by starting this concept, capacitor, it is an arrangement of two conductor separated by a insulator or dielectric. One important use of the capacitor is to store charges. Okay. Uses, it is an, I have told you, it is a device which store the arrangement of two conductors. Okay, the arrangement of two conductors separated by a dielectric. I have said it, separated by a, this is a positive and this is negative, separated by a dielectric. One important use of capacitor is to store the charges. Okay, this is all about the capacitor and capacitance of the conductor. Okay, I have said you that capacitance is a ratio of charge on the capacitor to the potential. Okay, the potential difference between the two conductors of the capacitor is called as capacitance of the conductor. So dear students, uh, today we have discussed about what is electric conductor, the properties of electric conductor, the what is capacitor and what is capacitance, how it will be denoted, and what is the SI unit of capacitor, and what SI unit of capacitance of the capacitor, and its dimensional formula and its notation. I mean how it will be symbols, how it will be denoted by the symbols for a fixed capacitors as well as for a variable capacitors. So in tomorrow's session, I mean in next session, capacitance of the some simple capacitors. So the application whatever they have applied in the syllabus to you. So I am going to discuss in the next session. By this I am going to wind up the session today itself. So I hope this concept is very very clear to you. And please read every day and don't waste your time. This is a precious moment for your all the career. So throughout the academic year, don't waste a minute. Have some discussion about the concepts related to your subject. This is a very important stage of your students. So don't waste your time. Start preparing for whatever you are preparing for. So by saying this, I'm going to end up this session today itself. In tomorrow's session, let me discuss further. So thank you.